The topic of this video will be conjugate additions. Reactions that fall in this class involve the nucleophilic addition to a conjugated double bond, hence the name. These reactions are also often called Michael additions or 1,4 additions. The most common electrophile for this type of reaction is an alpha-beta unsaturated carbonyl. Alpha-beta unsaturated carbonyl compounds are unusually electrophilic due to resonance. The carbons of the alpha-beta unsaturated carbonyl that are electrophilic are the carbonyl carbon and the carbon at the beta position to the carbonyl. When a nucleophile reacts with the carbonyl carbon, we get a tetrahedral intermediate that, once protonated, results in a substituted alcohol. Because the net reaction that has occurred is addition of a nucleophile and a proton on adjacent atoms, in other words, atoms 1 and 2, we call this mechanism a 1,2 addition. If instead the nucleophile attacks the beta carbon to the carbonyl, the other electrophilic position, we get an enolate. Once this enolate is protonated, we get an enol. Notice that the net reaction here is the addition of a proton and a nucleophile to the oxygen and the beta carbon, which are 4 atoms apart. Therefore, this is called a 1,4 addition. Remember that the enol under acidic or basic conditions will tautomerize to give the keto form. Therefore, the overall addition for a 1,4 or Michael addition is the addition of a nucleophile to the beta position of a carbonyl. In a conjugate addition, the conjugated double bond that acts to accept. In a conjugate addition, the conjugated double bond that acts as the electrophile is called the Michael acceptor because it accepts the electrons from the nucleophile. The nucleophile is called the Michael donor because it donates the electrons to form the new bond. Michael acceptors are typically alpha-beta unsaturated carbonyl compounds or other electron-poor alkenes. For example, conjugated aldehydes, conjugated ketones, conjugated esters, conjugated amides, conjugated nitriles, or conjugated nitro compounds. Michael donors include many of the good carbon nucleophiles we have previously discussed, such as Gilman reagents, enamines, and enolates, such as those of a beta diketone, beta ketoesters, beta ketonitriles, or alpha nitroketones. Finally, let's consider the mechanism for the addition of a Gilman reagent to an alpha-beta unsaturated ketone. Typically in these reactions, the alpha-beta unsaturated ketone or other Michael acceptor is treated with the Michael donor, in this case a Gilman reagent, followed by aqueous acid, which is necessary for the tautomerization step. In the first step of the mechanism, the Gilman reagent attacks the alpha-beta unsaturated ketone, forming the enolate. Following the addition of acid, the enolate is protonated to form the enol. The enol then undergoes tautomerization to the keto form. First, the ene is protonated to form a resonance-stabilized carbocation. In the final step, the protonated ketone is deprotonated by water to form the final substituted ketone product.